Today, we'll learn about sums of consecutive squares and sums of consecutive cubes, as well as how to derive their respective formulae. This video is the successor to an older video of mine, which had some issues, but you don't have to go watch that video. All you need to know is that this is the formula for the sum of consecutive integers from 1 to some number n. With that out of the way, let's get started. I think the first question that comes to mind is, where do we even begin? And if you're anything like me, the answer is that we need to emulate the Greeks and view things geometrically. Each of these squares has an integer side length 1 greater than the one to its left. This means that their areas are consecutive squares. So the sum that we're looking for is simply the cumulative area of these squares. In the case that we're looking at, this might seem very easy to simply do by hand, but as we sum more and more squares, this becomes less desirable. So while we're going to continue looking at this specific case, our goal is to find a generalization. Notice how each successive square sort of stratifies this shape into rows of distinct length. Since each row has a height of 1, we can find the total area by simply summing the lengths of each row. The key observation here is that each row loses a corresponding number of elements from the first row. So now that we know that, we can begin to employ algebraic methods. Now, just to avoid getting our workspace too cluttered, we're going to define some useful notation. S sub n is the sum of square integers from 1 squared to n squared, and r sub k is the total area in the kth row. Now we can write our sum in terms of these r sub k's, or rather, as the sum of r sub 1, r sub 2, and so on until r sub n. We can quite easily derive a formula for an arbitrary r sub k. It's the length of r sub 1 without the first k minus 1 squares. Let's use r sub 3 as a concrete example of what I'm talking about. R sub 3 is the same length as r sub 1 without the portions of that length contributed by the first two squares. We can further refine our formula for r sub k using the formula we touched on earlier. We finally have all the tools we need for the general case. Let's see what happens when we replace each r with its respective formula. We can begin simplifying this by factoring a 1/2 from the whole expression. Next, we can group the n squared plus n terms together. Since one of these terms was associated with each row, there are exactly n of them. We can further reduce things by grouping the negative terms based on whether or not they're being squared. One of these new terms is merely another sum of consecutive integers, but the other is far more interesting. It's almost identical to our original sum for lack of one term, namely n squared. We can therefore move this copy of our original sum to the left-hand side of the equation, leaving us with the fact that what remains on the right-hand side is 3/2 times the original sum. Let's simplify what we have left via factoring and gathering like terms, so that we're left with a cubic polynomial in n. At this point, we essentially have our sum formula. We can get s sub n by itself by multiplying both sides by 2/3. From there, all we have to do is factor the polynomial, and if you play around a bit, you'll find that it can factor into n times n plus 1 times 2n plus 1, leaving us with this result. Let's test this out on our earlier example, which we computed by hand to be 30. S sub 4 equals 4 times 5 times 9 all over 6, which reduces to exactly what we expected, 30. It's time to address the cube-shaped elephant in the room. We cannot approach this geometrically, at least not in this video. Instead, we're going to use what I think is a more interesting approach, and to adequately introduce the idea behind it, we're going to have to go back to sums of integers for a moment, particularly to explore what happens when we split these sums by parity. The even case is pretty straightforward. If we express the largest element of our sum as 2n, then simply factoring a 2 from each term in the sum returns the original sum formula, which we can simplify to n squared plus n. Now, to address the odd case, we can simply take a given sum of integers and remove all of the even terms. If we choose to express the largest element of this sum as 2n plus 1, then we can algebraically express the sum of consecutive odd integers as follows. This expression quite easily simplifies down to n squared plus 2n plus 1, which you might recognize as n plus 1 quantity squared. This identity leads us to the interesting fact that any square number can be represented by a sum of consecutive odd integers. And what's particularly relevant to us about this is that n squared is exactly the sum of the first n odd integers. There's a nice way to visualize this using these cute little L-shaped pieces called gnomons. This begs the question, can cubes be expressed in a similar way? And the answer is yes. Let's express n cubed as a sum of n odd integers. We'll take an arbitrary odd number x as the first term of the sum. Each subsequent term is 2 more than its predecessor, meaning that each term in the sum can be expressed in relation to x. This means that there's one x associated with each term in the sum, so once again, there are exactly n of them. So n cubed equals n times x plus the sum of evens from 2 to 2n minus 2, which we just derived a formula for. Expanding and contracting the equation leaves us with this. We can now solve for x, which will lend a bit of concreteness to what we're working with. Let's rearrange the equation to get x by itself and divide both sides of the equation by n. Now we have an exact value of x in terms of n. Next, we'll determine the bounds of the sequence that we're summing. We know that the lower bound is x, and earlier we saw that the upper bound was x plus 2n minus 2, so let's express those purely in terms of n. What we want to do with these is compare them to the bounds of the next sum. More specifically, we want to compare the upper bound of this sum to the lower bound of the next sum. By doing so, we can examine the gaps between sequences, and hopefully find a sum formula for cubes. I'm sure you're tired of hearing it by this point, but let's simplify this expression. By squaring and combining like terms, we find that it reduces down to n squared plus n plus 1. This is notable because it's exactly 2 more than the upper bound of the previous sum. What this means is that a sum of consecutive cubes is equivalent to a sum of consecutive odd integers. And given that 1 cubed is 1, we can induct that the sum of cubes from 1 cubed to n cubed is equivalent to the square of the sum of integers from 1 to n. This is because the kth term in the sum of cubes contributes k terms to the sum of odd integers. So 1 cubed contributes 1 odd integer, 2 cubed contributes the next 2, 3 cubed provides the 3 after that, and so on. This equality is called Nicomachus' theorem. Or is it Nicomachus' theorem? Some of the pronunciation guides differed a bit on this one. Regardless, this theorem actually went somewhat viral last year. 2025 can be expressed as a sum of cubes. It's 1 cubed through 9 cubed. Anyways, using the sum of integer formula on the right-hand side of our equation, and doing a bit more simplification, leads us to this formula. N to the 4th plus 2n cubed plus n squared all over 4 is an equivalent representation for the sum of cubes, though perhaps this form, n plus 1 squared times n squared all over 4, is preferable. I think the natural follow-up question to all of this is, are there formulas for sums of higher powers? I think we'll save this for a future video.